I will just share the screen. Are you able to see the slides?
Yes, ma'am.
Okay. So let us start. Mm, Welcome to week 2 assignments of Introductory Organic Chemistry 2 by Professor Harina Chakrapani and Professor Neeraja Deshaputre. Myself Anisha Suresh, PMRF TA for this course from IIT Bombay. So last week we have discussed previous year assignment questions from week 1. You people are having any doubt regarding any of the questions that we discussed? There are no doubts. We can go to week 2 summary followed by solving previous year questions, assignment questions. So coming to the summary of week 2. So in week 2, sir have discussed regarding the electrophilic aromatic substitution in phenol, followed by electrophilic aromatic substitution, effect of electron donating group and electron withdrawing group, then nucleophilic aromatic substitution reaction, followed by a special topic Hammond's postulate and some essentials of IR spectroscopy. So coming to electrophilic aromatic substitution in phenol. So this is basically the mechanism. So we will be having this lone pair on oxygen which will participate in resonance. So this will pull here and this electron pair can push to this position leaving a negative charge here. This can again participate in conjugation. Then this double bond will break and a negative charge will be formed here. Then if we push this here, this double bond will break and a negative charge will be formed here. We can clearly see that the negative charge will be present at both the ortho positions and the para position. So the aromatic substitution reaction in phenol will take place at the ortho and para positions. Now coming to the effect of electron donating and electron withdrawing group. So we have seen several examples of electron donating group, withdrawing groups and their effect in electrophilic aromatic substitution reactions. So this is the summary of the activating effects and directing effects of electron donating and withdrawing groups. So if you are having electron donating groups like NR2, OR, etc., they participate in donation by conjugation. So these groups are very activating groups and they are ortho and para directing only. In the case of alkyl groups can participate in this electrophilic aromatic substitution by donation by inductive effect. Alkyl groups can participate by donation by inductive effect. They are also activating in nature. They are mostly ortho and para directing, but in some cases they can be meta directing as well. In the case of halogens like fluorine, chlorine, bromine, and iodine, they can participate by donation through conjugation because of the lone pairs that are present here, and withdrawal by inductive effect because of the electronegative nature of these groups. So they are deactivating in nature, they are ortho and mostly para directing. And in the case of CF3, NR3 plus, etc., these are electron withdrawing groups. So they participate, their electronic effect will be withdrawal by inductive effect. They are deactivating in nature and they direct at meta position only. And in the case of nitro, cyano, COR, SO3R, etc., they their electronic effect will be withdrawal by conjugation. They are very deactivating in nature and they direct to meta position only. Okay, so this is the summary of the directing and activating effects of various electron donating and electron withdrawing groups. So this is what we have to keep in mind while solving electrophilic aromatic substitution reaction. Now coming to nucleophilic aromatic substitution reaction. So two types of mechanism we have learned for nucleophilic aromatic substitution reaction. The first one is addition elimination reaction mechanism, where a nucleophile will add to this position, where this position which is known as the ipso position. Then this double bond will shift here and this will shift here if we are having some electron withdrawing groups like this. And uh, when this charge is coming back, that is this O minus will shift here, this double bond will shift here, this will shift here, and this chloride which is a better leaving group, it will eliminate, keeping the OH. So here a substitution reaction have taken place. Chlorine is substituted by OH. So this is the addition elimination reaction mechanism, nucleophilic aromatic substitution reaction. The next mechanism is the benzene mechanism, where a benzene intermediate will be formed and then the addition will be taking place. So in this case, if we are having NaNH2 liquid ammonia etc, NH2 minus base will be formed. It will abstract the proton, which will create a negative charge here. Okay, then what will happen, this negative charge can shift here, and this bromide which is a good leaving group, it will eliminate, leading to formation of a benzene. This is very reactive intermediate, very reactive and unstable intermediate. So it will undergo further reactions at a faster rate. So we will be having nucleophiles like NH2 minus, which can attack at this position or this position. So if it is attacking at this position, this one of the double bonds will be breaking and it will shift here, and this negative charge can abstract proton from ammonia, leading to formation of this aniline. So this is the benzene mechanism. So in nucleophilic aromatic substitution reaction, you have to keep in mind the addition elimination reaction mechanism and the benzene mechanism. So you will be able to solve any problems that will be coming from nucleophilic aromatic substitution reaction. Now coming to a special topic, which is the Hammond's postulate. So here, if we this Hammond's postulate will give information about the structure of the transition states. So if we are having two states which can interconvert and they are closer in energy, then their structure will also be similar. It says that two states that interconvert directly are directly linked in a reaction profile diagram, and that are close in energy are also similar in structure. So, a transition state will be most like the starting material, the intermediate, or the product if it is close in energy to one of these observable structures. So, if we are having the transition state which is closer to energy, to that of the intermediate or starting material or product, so the transition state will be identical to that. Okay, whichever it is closer in energy. So that is the Hammond postulate. And for keeping in mind, if the reaction is highly endothermic, this transition state will resemble the product. So if we are having an energy diagram like this is endothermic reaction, this is the starting material and this is the product. So this is the transition state. So trans transition state is closer in energy with that of the product, so it will resemble the product. And in this case, for a highly exothermic reaction, the transition state resembles the starting material. So in the case of exothermic reaction, the profile diagram will be like this is the starting material, this is the product. So the transition state which is here, it is closer in energy to that of the starting material, so it will resemble the starting material. So this is what we have to tell about the Hammond's postulate. Now coming to essentials of IR spectroscopy. So for understanding the IR spectroscopy, the important equation that you should remember is that the frequency nu will be equal to 1 by 2 pi root of k by nu. Okay, 1 by 2 pi root of k by nu, where k is the force constant and mu is the reduced mass, which is m1 m2 divided by m1 plus m2. Mu is the reduced mass. So if we are having idea about this equation, then we can easily solve any problems that will be coming from IR spectroscopy. So if the force constant, when we are talking about the force constant, we can correlate it with the bond strength. So if the force constant is increasing, then the frequency will increase. So if the bond strength will increase, then frequency will increase. This K can be correlated to bond strength. So if the bond strength is increasing, frequency will increase. So if we are having a triple bond, its frequency will be greater than double bond, which will be greater than the single bond. And if the reduced mass is increasing, the frequency will decrease. Okay, so if we are having lighter atom, then the frequency will be more. So this is what we have to remember about IR spectroscopy. And so this is one small chart uh, which will give an idea about where the peaks will be coming in IR spectrum. So as we have learned, these single bonds, it will be coming around lesser frequency compared to double bonds, compared to triple bonds. Triple bonds are coming in higher frequencies. So this is coming around the region 600 to 1400, and this is known as a fingerprint region. So this will be difficult to interpret. So we will be mainly focusing on this part while we are interpreting the IR spectrum. So the alkene peaks like C double bond C, C double bond O, C double bond N, it will be coming around the region of 1600 to 1800. And this triple bond C, triple bond C, C triple bond N, that will be coming around the region of 2000 to 2500, as you can see here. And and when we are having lighter atoms like hydrogen, that stretchings will be coming in the region of 2500 to 3500, like NH, OH, CH, it will be coming in this region. Okay. So for further references, you can follow Claydon Organic Chemistry chapters 22, 23, and chapter 3. Now coming to the previous year assignment questions. So this is the first question. The order of reactivity in the following series of compounds, where X denotes substituents indicated in the option below. So here X equal to nitro, cyano, COMe, and Me. So the order of reactivity of the compounds, if X is these, towards nucleophilic aromatic substitution. So what will be the order? A. Yes, A is the right option. So we can see the mechanism of this nucleophilic aromatic substitution reaction. So here the NH will be attacking at this ipso position of the fluorine. This will shift here and this will come here. So here a negative charge will be coming. If it can be like this as well, okay? Fluorine X. So here a negative charge will be there. So whatever can stabilize this negative charge, it will lead to faster rate of the reaction. So more stable the intermediate, lesser will be the energy barrier towards its formation. So the intermediate should be stabler, and more the electron withdrawing ability, it better stabilizes the negative charge. So here there is a negative charge. If there is an electron withdrawing group here, it can reduce this charge density. If the charge density is decreasing, then it will become more stabler. Okay. So in the case of nitro, cyano, COMe and Me, nitro is a better electron withdrawing group, so it will stabilize more. Then comes cyano, then comes COMe, and at last Me. Me is not much electron withdrawing in nature. So that is why the right answer is option A. NO2 greater than Cn, greater than COMe, greater than Me. Is this clear? Hello? Is this clear? Okay. Now coming to question number 2. Which of the following mechanisms of action occur when there are electron withdrawing groups on the aromatic ring during nucleophilic substitution? Addition elimination, elimination addition, substitution addition, addition substitution. So if such a system is there, what is happening there? Electron withdrawing groups are there and a nucleophilic substitution is taking place in the aromatic ring, then what is the mechanism that it is following? Yeah, it is following addition elimination. First of all, this OH minus will add at this ipso position where this chloride is present, then this double bond will shift here and it will conjugate to this electron withdrawing group. Then once this is coming back, this chloride, which is a better leaving group, it will be undergoing elimination. So the mechanism that it is following here is addition elimination. Clear? Any doubts? If there are no doubts, we can move to question number 3. Here, determine the product in the given nucleophilic aromatic substitution reaction. So this is our starting material. Okay, this is the starting material. It is treated with EtNH2 in the presence of heat. So what is the product that will be formed? Out of these 4 options, what is the right option? So what sort of mechanism will be taking place here at first? This is a nucleophilic aromatic substitution reaction. So which mechanism it is undergoing? Is it addition elimination or is it through Benzyne mechanism? Anyone? So here, since there is an electron withdrawing group like nitro, it will follow addition elimination reaction. Okay. So what will be the product? If you will say like this, it will be confusion for me. I will number it A, B, C, D. Now, what is the product? B. Yeah, it is the right answer. So in this case, we have told like it is addition elimination reaction. So here the nucleophile will be NH2 minus. NH2 minus will add to ipso position of the chlorine. As you can see here, NH2 minus will add to ipso position of the chlorine. It can this double bond will shift here, which can shift here it will undergo maximum possible conjugation. So this intermediate will be formed, and once this will come back, this Cl minus, which is a better living group, it will eliminate and we will get this product. So this is the product that we will get. Any doubt? There is no doubts. We can go to question number 4. Coming to question number 4, the major product of the following reaction is. So here 2-fluoroanisole is there, and acetic anhydride is given, and the reagent that is given is AlCl3. So what is the reaction that is taking place here? From the reagents given, what is the reaction that is taking place here? You can see AlCl3 and acetic anhydride. Yeah, Friedel-Crafts acylation reaction is taking place here. So what is the major product that will be forming? Yeah, acylation. Friedel-Crafts acylation reaction is taking place here. So what is the major product? Yeah, C. So we will take into consideration this OCH3, and based on that the para position, the acylation will take place. Okay. So the right answer will be option C, and we will see the mechanism. So in the case of acetic anhydride, it will coordinate with AlCl3 and this intermediate will form. Then this oxygen lone pairs will push here and this bond will break and we will get the acylium ion, which is the intermediate, reactive intermediate for acylation reaction. Okay, and this will be byproduct. So this acylium ion, and this is our starting material. So this lone pairs, it will push here, this double bond will break and the bond will shift here and this bond will go and attack at this carbon, and this bond will neutralize the positive charge on the oxygen and we will get this intermediate. Okay. Now in the presence of the base, this proton will be abstracted so that the aromaticity will be regained. So this proton will be abstracted and it will shift here. This bond will break and it will shift here, and CH3 will be neutralized. So this is the product that we will get. Okay. Is the mechanism clear? So the product is option number C. Now coming to question number 5. The structure that contributes the most towards stability of cationic intermediate during bromination is. So different cationic intermediates for bromination of this aniline, uh, N-dimethyl aniline is given. So out of which the structure that mostly contributes towards the stability of cationic intermediate is what? Yeah, option D will be the right answer. So if we see the mechanism of the bromination, we can see like and then dimethyl aniline will be there. So this lone pair will shift here. It can this bond will break and a negative charge will be formed here. When this negative charge will undergo conjugation, this bond will break and a negative charge will be formed here. And if this is shifting, and this bond will break and a negative charge will be formed here. So in the case of bromination, so this is the cationic intermediate that is forming, and we are having negative charge at this both ortho position and the para position. So this is the key intermediate that is formed here. And as per the question, if we are getting other intermediates what they have given here, so the NME2 will not be participating, and just this bond will be breaking, and it will be attacking the Br2, and we are getting bromination. So that is basically what they are given in the options. So this will not be basically taking place because this lone pair of NME2, this lone pair will take part, and hence it will be orthopara directing. So this is not the right mechanism. So this intermediate that will be formed here where double bond NME2 is there, that is a cationic intermediate that is mostly contributing towards the stability of the cationic intermediate. Okay. So option D will be the right answer. Now coming to the question number 6. Identify the reagents for the following transformation. So benzene is there. Then we have done acylation. We got um, acetophenone. And then we have done chlorination. Chlorination reaction. So what is the reagents that is used here? Followed by then we reduce this ketone to alkane. So, what are the reagents that are used in A, B, and C? So, some options are given, out of which what will be the right option? Option number A. Yeah, it could be the right answer because here Friedel-Crafts acylation reaction is taking place as per the reagents. That is right. Followed by this COCH3, it is a meta-directing group. So, electrophilic aromatic substitution in the presence of COCH3, it will direct the Cl2 to meta position. So, these reagents are right. Followed by Clemmensen reduction, as we have seen in the last lecture, where this C double bond or CH3 will be reduced to alkene. So, option A will be the right answer, and you can see the mechanism here. So, we are having the alkyl chloride, acyl chloride. In the presence of AlCl3, chlorine will coordinate with AlCl3. Then the lone pair on oxygen will shift here, and this will AlCl4 minus will leave, leading to formation of the acylium ion. Then the benzene double bond will go and attack at this carbon, and this bond will break and neutralize the positive charge on the oxygen. Now, in order to regain the aromaticity, Cl minus, which will be present in the medium, it will abstract the proton, and it will neutralize the positive charge that will be formed while benzene will be attacking the acylium ion. So we will get this acylation product. So this is the mechanism for Friedel-Crafts acylation. And for aromatic electrophilic aromatic substitution, so in the presence of FeCl3 and Cl2, the benzene, in this case we will be having COCH3 in benzene. So it will go and attack the chloride Cl2 that is coordinated with FeCl3, and this FeCl4 minus will leave, and we will get this, and this proton will be abstracted in order to regain the aromaticity. So that is how electrophilic aromatic substitution or chlorination reaction will take place. And finally, Clemmensen reduction will take place, where the ketone in the presence of zinc mercury amalgam, it will be converted to alkene. So clear, right? Now, as you have told, option A is the right answer. Now, coming to question number 7. The increasing order of reactivity of the following compounds towards electrophilic aromatic substitution is. So you can remember the chart that I have shown in the summary that we discussed today. So from that you can understand. Methyl groups are activating in nature, while halo compounds like fluoro is deactivating, and this electron withdrawing aldehydes will also be deactivating in nature. So, based on that, what will be the increasing order of reactivity of these compounds towards electrophilic aromatic substitution reaction? B, yeah, B will be the right answer. One will be mostly like it will be having the highest reactivity as all these positions can, like these three positions can react. So this is the ortho position, this is the para. So for this is the ortho position, this is the para. So all these positions will be reactive, but in this case only the ortho positions could react. Para position is not activated. Okay. And in case of fluoro and the CHO, since this can participate with inductive effect, donation, conjugation effect, but this will be electron withdrawing in nature. So this will be little deactivating, but this will be very deactivating. So that will be the right order. Now coming to next question. What is the major product of the following reaction? So here nitration reaction is given and our starting material is this. So what will be the major product? They are asking for the major product. For nitration reaction, like in the presence of this bromo, it can direct to both ortho and para. But what will be the major product? Ortho para directing, but para will be the major because of sterics factors of ortho. Okay. So what will be the major product that is forming here? I will give options A, B, C, D. Yeah, D is the right option. So the mechanism will be like this. Lone pairs of bromine will involve in conjugation. This double bond will shift here. This will shift here. This bond will shift here. And this bond will go and attack the nitrosonium ion. That will be formed by reaction of HNO3 and H2SO4 that we have seen in the last lecture. So we will get this intermediate. Now if the base not BH. The base will be coming and abstracting this proton for regaining the aromaticity. So this will shift here, this double bond will shift, and this double bond will shift here, this will shift here, and the positive charge on the bromine will be neutralized, and we will get this as the major product. But minor product could be there where substitution like nitration reaction can take place at this position or this position. Okay, and it can take place at this position or this position as well, based on the uh, like wherever negative charges coming, the in all that positions nitration can take place, but the major product will be this one. Okay, so this is the right option. Now coming to question number 9. The following reaction yields. So here 2 chloro is given and it is treated with NaNH2 liquid ammonia. So the mechanism that it will undergo is benzene type mechanism. Okay, this we have seen in the lecture. These substrate, if it is undergoing reaction with NaNH2 liquid ammonia, it will undergo benzene type mechanism where the benzene intermediate will be formed. So what is the major product that will be formed here? What is the major product that is forming? A, B, C or D? Yeah, B will be the major product that will be forming. We can see the mechanism. So in the presence of NaNH2 liquid ammonia, NH2 minus base will be forming. So it will abstract the proton that is to this chloride. So it will abstract the proton and benzene intermediate will be formed when the Cl minus will leave. So this is the benzene intermediate that is forming. So now we are having NH2 minus as the nucleophile. Sorry. This NH2 minus can attack at this position or this position. Okay. So if it is attacking at this position, this pink labeled position, so this intermediate will form. This bond will break, it will shift here, and this negative charge will be formed. And this OMe by electron withdrawing effect, it cannot stabilize this negative charge by electron withdrawing effect of this OMe. Electron withdrawing inductive effect of this OMe, it cannot stabilize this negative charge, as well as this NH2 will be creating some steric interaction with this OMe. So this product that will be formed will be minor. Okay, if it is forming, it will be minor. When this is attacking at this blue position, this double bond will shift here, a negative charge will be formed here. Since this OMe is closer to that of the negative charge, or the negative charge is adjacent to that of OMe, because of the electron withdrawing inductive effect of this OMe, this negative charge could be stabilized, as well as now there is no steric interaction between this OMe and NH2. So this will be the major product that will be formed. So in our question they have asked for the major product. So this is the major product that is forming in this reaction. So option B is the right option. Clear? Any doubts?
Madam, I have one question.
Yeah.
Madam, kindly show the mechanism you have explained just earlier.
Okay, okay.
So you said that
Hmm.
if the NH2 group, if it is attacked at ortho position,
Yeah.
then it provide the carbon, it provide the anion intermediate, and
Yeah.
it is quite stable as compared to the meta attack.
This negative charge.
Yes, this negative charge.
This is
But
not
if
stable. It could not be
uh,
stabilized by the electron withdrawing effect of this OMe. Because this is
no,
far
ma'am,
away
but
from
if
OMe, it could not be stabilized.
okay, if we consider that the negative charge is formed at ortho position, it is
Hmm.
stabilized
Hmm.
by minus I effect, isn't it?
Yeah.
But there is a predominant effect that is we can say it is a plus R effect, that is resonance effect. So it will destabilize that ortho anion more effectively. Can we think like this?
Okay.
Because the plus R effect it is predominant as compared to minus I effect.
Huh,
And
huh.
as far as my I am thinking like that, like this way.
Hmm. That could also be possible. But the sterics is also considerable, right?
But how we can say that it is a major product, ma'am? If we consider the predominant, if predominant effect is plus R as compared to that what we can say steric hindrance,
Okay.
then the uh,
I
meta
would like to
ion
explain.
it is quite stable because it
Hmm.
plus R effect, by plus R effect it reduces the electron density at meta position, therefore it is I think it is more stable as compared to
You are telling
the
this is
ortho
stable.
anion.
Okay. Otherwise, we can tell like if the intermediate that is formed is more reactive, it will lead to the major product, right?
Yes,
If we consider these two, out of which, according to you, this is unstable.
first one should be the major product.
This is unstable
That
according to you, right? Because of the plus R effect,
yeah,
this will be unstable because of the larger negative charge here. So unstable one will be reacting faster, so it will lead to the major product. Like whatever reacting faster, it can react fast and give the product at faster rate, right? So if this product
no sir,
is forming
ma'am.
at faster rate, then
No, no, ma'am. The question is that you showed that minor product is the ortho amino and major product is the meta amino.
one. Hmm.
But instead of that minor product of ortho amino, it should be a major product, and the major product it should be minor product. If we consider that the meta ion, which is intermediate ion, when the NH2 is attacked at ortho position, that meta ion is more stable
Hmm.
because if the methoxy group, if it exert its plus R effect, then the electron density at meta position will be more less. But if it is attacked at
Hmm.
ortho position, sorry, at meta position, then the intermediate ion is formed
And
where the
here there
negative
will
charge
be
is
more
position.
negative charge. Yeah.
Yeah. Yes, and if that plus methoxy group, if it exert its plus R effect, then it increase the electron density more at
Hmm.
ortho position. Therefore, it destabilize it, and activation energy is more for that meta attack.
Intermediate, yeah.
Yeah, I am thinking
According to
like that way. It
activation
may be wrong.
energy concept, the intermediate that is found, this will actually you are telling this will be lower in energy, and this should lead to the major product.
Yes, yes.
Maybe I think then sterics will also be uh, like giving major influence. That is why this is the major product. Sterics is also playing a part. We have seen while we are learning the electrophilic aromatic substitution reaction, out of ortho and para, we will be getting para product major, right?
Yes.
Because of the steric factor. Even though, according to statistics, we should get ortho product major. Like it is
Okay,
in
ma'am.
the ratio of 2 is to 1. We are expecting ortho should be more and para should be less. But because of the steric effect of the ortho, it is giving the para product major. Maybe that is the
Yes,
major,
ma'am.
factor that is influencing this reaction, and it is leading to this as the major product. I think so.
Okay, ma'am. Okay, okay. Thank you, ma'am.
Okay. Yeah, it could be exception as well. If I could find a other reasonable answer, I will share it in the next lecture. Okay.
Okay, ma'am. Okay.
Mm. So according to now, option B will be the major product that is formed in this reaction. Now coming to question number 10. Which among the following compound will not react under the standard Friedel-Crafts alkylation reaction condition? So different type of chloride is given, as you can see here, out of which one of the compound will not react under Friedel-Crafts alkylation condition. So which one it will be? 1, 2, 3 or 4?
It should be one.
Yeah. What could be the reason?
uh, if that vinylic chlorine, if it undergoes, if it leave from that
Hmm.
vinylic carbon atom, then it results into the formation of the carbocation
Hmm.
that cannot be stabilized by resonance effect, because their geometry cannot be matched.
Hmm. Hmm.
The pi bond is what we can say, it is vertical, and the carbocation orbital, it is horizontal, so they cannot be overlapped.
Yeah. So vinyl carbocation formation is not favored. So because of
Yeah.
that, the Friedel-Crafts alkylation reaction will not take place.
Yes, ma'am.
Hmm. That is the right answer. So for so this will come under the limitation of Friedel-Crafts alkylation. As you can see here, the carbocations that are formed from the aryl and vinyl halides are extremely unstable, and because of this, the reaction will not it will not undergo reaction. So here, if the carbocation is forming, it will be the vinylic carbocation, as you can see here. So this is extremely unstable carbocation, and because of that, it cannot undergo Friedel-Crafts alkylation. And some other exceptions, as you can see, the presence of a deactivating group on the aromatic ring like NH2 group, it can lead to deactivation of the catalyst due to formation of complexes. One of the question that we have discussed in last lecture, as you can see, further in aniline case, uh, Friedel-Crafts alkylation reaction was not taking place because it was this AlCl3 was forming complex with this NH2 group. And another limitation of Friedel-Crafts reaction is that we should use the aromatic compound in less amount, so as to avoid polyalkylation. The excess amount. The excess of aromatic compound must be used in this reaction in order to avoid polyalkylation. If uh, this alkyl substituents are more, in that case polyalkylation reaction can take place. In order to avoid that, we should use this aromatic compound in excess amount, and aromatic compounds that are less reactive than monohalopentenes, they do not participate in Friedel-Crafts alkylation reaction. So these are some limitations of the Friedel-Crafts reaction, and this first option is the reason why this aryl or vinyl halides and our this substrate one is not taking part in Friedel-Crafts alkylation reaction. Okay.
Yes, yes.
Now coming to question number 11. Which one of the following undergoes nucleophilic aromatic substitution at a fastest rate?
Option number one.
Option number 1. Because as we have seen in nucleophilic aromatic substitution, a negative charge will in the intermediate, a negative charge will be formed here, and this electron withdrawing ability of the group that is present here, it will determine how stable the intermediate is and how fast it can lead to formation of the product. So in this case, the nitro, it can stabilize a negative charge, it will be formed here. Nitro is more electron withdrawing in nature compared to chloro, CH3, OCH3, etc. In case of OCH3, CH3, these are electron donating type of groups as per here as per inductive effect, and this as per resonance effect. These are electron donating in nature, so it will destabilize a negative charge that will be formed here. So in case of nitro, the negative charge that will be formed here will be stabilized because of the electron withdrawing ability of the nitro group. Hence the intermediate will be stabler and the reaction will take place at a faster rate.
Yes, ma'am. Yes, absolutely right.
Now coming to question number 12. Which position will be attacked most rapidly by the nitronium ion NO2 plus when the compound undergoes nitration with HNO3 and H2SO4? So this is the compound that is given, and they have labeled some four positions, out of which position will be undergoing rapid nitration reaction.
At position D.
Yeah, it is right. So this OCH3 is most activating towards the electrophilic aromatic substitution reaction. So this is most activating in nature, and it can undergo nitration reaction at ortho position or para position. So here the para position is hindered by the presence of this uh, C double bond O group, CH3 C double bond O group, and hence this D position will undergo nitration. Okay. Now coming to question number 13.
Ma'am,
Uh,
kindly go on previous question.
yeah.
Ma'am, the nitronium ion, it can be attacked at position, at para position.
Para position of
If
which one?
of yes, behind the C, on methoxy group containing ring.
Here.
Yeah.
But aromaticity will be lost, right? So that will not be
Yes.
favored.
Okay. Okay.
Hmm. If it is coming here, then aromaticity will be lost. Now coming to question number 13. Some meta-directing substituents in aromatic substitution are given. Which one is most deactivating? So we have seen in the summary that we have discussed today.
Option number one.
SO3H. Nitro will be more electron withdrawing, right? Compared to SO3H.
I think, ma'am, SO3H, it is more deactivating as it contains two S double bond, sulfur and oxygen double bond. So it may delocalize over two.
I think NO2 will be more deactivating. I will check and get back to you, okay? Yes, double bondo, OH. You are telling like it can undergo delocalization to both these positions, so there should be more deactivating. I will check into it and get back, okay? I think as of now it should be NO2. This we will check. Now coming to question number 14. For the sequence below, identify X, Y, and Z. So this fluorobenzene, it is treated with HNO3 and H2SO4, and X substitution is taking place here. So what is X? And this compound is treated under the condition Y, and it is giving this fluoroaniline. And this compound is treated under Z condition, and this NH2 is substituted by CN, and further nucleophilic aromatic substitution reaction by addition elimination is taking place and we are getting this product. Okay, so what is X, Y and Z? HNO3 H2SO4, here what is taking place? B. Yeah, here nitration reaction is taking place under this condition, and at para position of fluoro nitration is taking place, and so X will be NO2 and Y, this NO2 is reduced to NH2. So for that we can use H2PDC condition, and this compound set is converted into CN. So first diazotization reaction will be taking place under NaNO2HCl, and when we treat it with CuCN, this nitrogen will be replaced with Cn minus. Okay, so option B will be the right answer. And for the mechanism, you can see this is the mechanism for nitration reaction as you have seen. So here if fluorine is there, at ortho position or para position of fluorine, nitration can take place. So this is the mechanism for nitration. In the presence of nitric acid and sulfuric acid, nitronium ion will form first, and the double bond will go and attack on the nitronium ion, followed by abstraction of this proton by the presence of some base in the medium, and we will get the nitration product. And if we treat with H2PDC condition, NO2 will be reduced to NH2, and the NH2 when we treat with NaNO2HCl condition, diazotization reaction will take place and N2 plus will be formed here, and when we treat it with Cn minus, it will attack here and this N2 minus will be leaving. Okay, N2 minus will be leaving by addition elimination reaction. So that is the answer, option B. Any questions? 14 question.
Ma'am, 13 number.
Okay. 13 we have to check. I think it should be NO2 because of the electron withdrawing ability of NO2. As we have seen in the electron withdrawing ability chart, NO2 is the greatest electron withdrawing, NO2 will be having the greatest electron withdrawing power. But according to what you have tell, like because of the presence of these two double bond O, SO3H could also be withdrawing, and it should be most deactivating. That I will check into, okay?
Madam, due to the two double bond, the negative charge may delocalize over both the double bond. Therefore, it is more stable,
Yeah.
I think.
Huh.
And in case of NO2, there is only one nitrogen oxygen double bond where that negative charge can delocalize.
Yeah.
So it's delocalizing. So it's stabilizing ability of SO3H. I think it should be greater than
That is
NO2.
NO2. Yeah, I understand your concern. I will check into it and I will update. Okay. In the next lecture, I will tell.
Yes, ma'am. Thank you, ma'am.
Okay. So this question, is that clear? So here HNO3 H2SO4 is given. Fluorobenzene is treated with HNO3 H2SO4. One reaction is taking place. Electrophilic aromatic substitution reaction is taking place, and an X is introduced here. And this compound is treated under the condition Y, and we are getting NH2. And this compound is treated under the condition Z, and we are getting CN. And this will undergo nucleophilic aromatic substitution reaction, and this fluorine is getting replaced by NME2. So as we discussed, This X could be NO2, as this is electrophilic aromatic substitution with or nitration reaction. Then this NO2, it is reduced to NH2. So the condition that could be used here is hydrogenation, that is H2PDC condition for reduction of NO2 to NH2. And this NH2, it is converted back to this NH2 is converted into CN. For that, first diazotization reaction will be taking place. N2 plus will be formed, followed by treatment with CuCN. We will get cyano in place of N2 plus. Then we are following nucleophilic addition elimination reaction. So we are getting this product. So the right option could be option B. Is that clear?
Yes, ma'am. Yes.
Okay. Now coming to question number 15. Arrange the reactivity of the given compounds in decreasing order for addition followed by elimination reaction. So we are having fluorine, chlorine, bromine, iodine. So this I have discussed in the lecture. So the electron negative ability of the groups are considered here for stabilizing the intermediate. So what will be the right order? Option 4. Yeah, option 4 will be the right answer. We will see why. So here, in our case, this is CHO and it is para. Okay, but this is for the example. So for the addition elimination reaction taking place, if fluorine is there, the intermediate that will be formed, that will be stabilized by the electron negativity of the fluorine. Negative charge of the intermediate, it will be stabilized by the electron negative ability. Fluorine will be electron withdrawing in nature, electron withdrawing inductive effect. Fluorine in fact slow down the second step relative to Cl minus A, but it accelerates the first step. First we will be thinking fluorine is of lower fluorine is small in size, removal of fluorine will be difficult. Because of that, iodine should be more reactive, we will be thinking. But the acceleration of the first step by fluorine is affecting the fastest of the making the reaction faster. Okay, fluoride does in fact slow down the second step relative to Cl minus, but it accelerates the first step simply by its enormous inductive effect. It is the most electronegative element of all, and it stabilizes the anionic intermediate, assisting the acceptance of electrons by benzene ring. So in our case, we are given this compound, fluorine CHO. So here, addition elimination reaction it is given. So a nucleophile is coming, it is attacking here, and a negative charge will be formed here, right? Fluorine, nucleophile, CHO minus. So here the electron withdrawing inductive effect of the fluid, because of the electron withdrawing inductive effect of fluorine, this negative charge on the intermediate will be stabilized. Hence this first step will be faster, and because of that it will enhance the rate of the reaction. Okay. The fluoro compounds react approximately 10 power 2 to 10 power 3 times faster than chloro and bromo compounds. So option 4 will be the right answer. Is it clear? Okay. Now coming to question number 16. So we have learned regarding the IR spectroscopy and this question is based on IR spectroscopy. What is the correct increasing order of stretching frequencies for C triple bond C, C double bond C and C single bond C? So for that we should remember this equation. Frequency F equal to 1 by 2 pi root of K by nu. So here this is the bond strength. So as bond strength increases, frequency increases. So for triple bond C, the bond strength is more compared to double bond and compared to single bond. So what will be the increasing order of stretching frequencies? Option B. Yeah, it is the right answer. So we can say F proportional to root of K, which is the force constant. So for force constant, we can correlate it with the bond strength. So bond strength will be of the like order triple bond greater than double bond greater than single bond. So the stretching frequencies will also be following that order. As the bond strength increases, stretching frequency also increases. So the right answer will be option B. Is this clear? There is no doubt. We can move to question number 17. So in the IR spectrum, carbonyl absorption band for the following compound appears at. So this is a question from CSIR net December 2011. So here a five-membered cyclic lactone is given and they are asking the IR spectrum. So what will be the value for this carbonyl absorption band? 1810 centimeter inverse, 1770 centimeter inverse, 1730 centimeter inverse, 1690 centimeter inverse. So for that we should know where the carbonyl frequencies are coming for different compounds. So this is the hint for amides, C double bond O NH2, the CO stretching frequency will come around 1680. For ketones, it is coming around 1715. For aldehydes, it is coming around 1725. For esters, carboxylic esters, it is coming around 1735. For carboxylic acids, it is coming around 1710. For acyl halides, it is coming around 1800 and carboxylic anhydrates. So it is coming around 1820, 1760. Okay. So the quoted frequencies are for typical open chain saturated hydrocarbon chains. Conjugation and cyclic structures will influence the absorption frequency. So in our case, we are having cyclic ester, lactone. So for that, what will be the value? So in the case of esters, we have seen like it is 1735. So it could be 1735 or 1740 plus minus 10 centimeter inverse for non-cyclic esters. But for the cyclic esters, for 6-membered lactone it is coming around 1740 plus minus 10. For 5-membered lactone it is coming around 1765 plus minus 10. For 4-membered lactone it is coming around 1840 plus minus 5. So in the question that is given to us, we are having a 5-membered lactone. So it is coming around 1765 plus minus 10 centimeter inverse. We are having 5-membered lactone. 5-membered lactone. Cyclic esters are known as lactones, okay? So from the option, so we are having 1765 plus minus 10 centimeter inverse for this 5-membered cyclic lactone. So out of this 4 option, what will be the right option?
Option B.
Option B will be the right option. Yeah, option B will be the right option. But for this course, I think we don't have to memorize all these values. Okay. Now coming to question number 18. The correct order of rates of bromination is. So we are given different alkyl benzenes and benzene. So what is the correct order of bromination for these compounds? Alkyl groups are activating in nature. It is orthopara directing. So in case of D, both these are ortho positions. This is para position. In case of this one, like for with respect to this group, this is ortho position. This is para position. In case of this, one of the ortho position will always be hindered. Okay. In case of B, this is ortho and this is para. So the right option for rate will be D greater than, B greater than, C greater than A. Clear? Here, one of the methyl group will be hindering either the ortho position of each other. Because of that, this is less, it will having less rater in bromination reaction. Is this clear? Can we move to next question?
Yes, ma'am.
Okay. Now coming to question number 19. The major product of the following reaction is. So here we are having this compound and it is undergoing bromination in the presence of acetic acid. So which of the group among CF3, NH2 and NO2 which will be directing bromine? From the chart that we have seen here, we have seen in the summary, CF3 and NO2 are deactivating in nature. And NH2, it is activating and orthopara directing. deactivating and meta directing. So what will be the major product that will be forming here? A, B, C or D? B. Yeah. Option B will be the right answer. So NH2, it could be orthopara directing. So this is the only position. So this is the only position that it can direct to. This is the only position that it can direct to. Both are ortho position. This is para position. These two positions are hindered because of CF3 and NO2 group. So this is the ortho position that is free and it will be directed to here. And we can see this is meta to that of NO2 and CF3. So this is the major product that will be forming. So this is the mechanism. NH2 lone pairs will shift here. This bond will go and attack the bromide. Br plus, Br minus will eliminate. This is the intermediate that will be formed. Then Br minus will abstract the proton and it will neutralize this positive charge on the NH2, leading to the formation of this product plus HBr. Clear?
Yes, ma'am.
Okay. Now coming to, so option B is the right option here. And coming to the last question of this assignment set, the product of the following reactions are. So here, Friedel-Crafts alkylation reaction. Alkylation reaction is taking place. So what is the major product and what is the minor product that will be forming here? Here this will act as the alkyl counterpart, okay? Here the formation of phenyl positive charges not feasible and formation of benzylic carbocation is more favored. So this will act as the alkyl counterpart. So what will be the major product and what will be the minor product? Option B. Major product is B, minor product is D. Yeah, that is the right option. So the alkylation reaction, this fluorine will direct to ortho position or para position. So the major product that will be formed will be para 1 because of the steric reasons of ortho, and the minor product that will be formed as D. So this is the mechanism. The chloride will coordinate with AlCl3 and it will form this intermediate. Now this fluorine lone pairs will push here. This double bond will shift. This double bond will go and attack at this position. This AlCl4 minus will leave and we will get this intermediate. Now for regaining the aromaticity, some base will abstract this proton and this positive charge on the, if you are telling like this, this positive charge will be neutralized and we will get this product. If ortho substitution is taking place, it will be like this. It will attack at this position. So F plus, now this hydrogen will be abstracted by the base and this positive charge on fluorine will be neutralized and this product will be formed. This is minor product. This is major product. So this is ortho directing, ortho, and this is para directing. So because of steric reasons, this will be the minor product and this will be the major product. Para 1 will be major product and ortho 1 will be minor product. Is this clear? Okay. So the right answer will be option B. So are you having any doubts regarding any questions that we have discussed? So that nitro SO3H question I will see and I will get back to you in the next lecture. Apart from that, is there any doubts? There are no doubts, then we can wind up today's session. Thank you for joining. We will see next Sunday. Thank you.